Hello everyone, in this lesson we will learn about the basic properties of probability. The learning objectives of this lesson are, firstly, to understand the properties of probability through examples. Secondly, master the algorithm for calculating the probability of random events and be able to use it to calculate the probability of random events. The focus and difficulty of this lesson is to be able to use probability algorithms to calculate the probability of random events. In the last class, we learned classical models. The two basic characteristics of classical models are finiteness and equiprability. Limitations refer to the limited number of sample points in a sample space. Equal likelihood refers to the equal likelihood of each sample point occurring. This is the calculation formula for classical models. We also learned about the relationships and operations of events earlier. Inclusion relationship refers to the occurrence of event A leading to the occurrence of event B, which we refer to as A being included in B. Compatibility refers to the occurrence of at least one of A and B. A cross event refers to the simultaneous occurrence of A and B. Mutual exclusion event refers to the situation where A and B cannot occur simultaneously. That is to say, the intersection of event A and event B is an impossible event. Opposing events refer to A and B having only one occurrence. That is to say, the intersection event of event A and event B is an impossible event, and the combination event is a necessary event. Obviously, ground events are a special case of mutually exclusive events. What perspectives should we study the properties of probability in this lesson? Generally speaking, once a mathematical object is defined, its properties can be studied based on the definition. For example, after learning the definition of exponential functions earlier, we studied the properties of exponential functions such as their definition, domain value, and domain monotonicity. These properties can play a significant role in solving problems. Similarly, after providing the definition of probability, we will study the fundamental properties of probability. For example, the range of probability values, the probability of special events, the relationship between their probabilities when events have certain special relationships, and so on. According to the definition of probability, we know that the probability of any event is non-negative. In each experiment, inevitable events must occur and impossible events must not occur. So we obtained property 1 and property 2. Now let's take a look at an exploratory question. Assuming that event A and event B are mutually exclusive, what is the relationship between the probabilities of events A and B and the probabilities of events A and B? Let's use an example to illustrate. There are 4 balls of the same size and texture in a bag, with 2 red balls labeled 1 and 2 and 2 green balls labeled 3 and 4. Randomly find 2 balls from the bag that are not returned. Let event R be equal to touching the red ball twice. Event G is equivalent to touching the green ball twice. The sum of R and G events is the same color as the balls touched twice, because it is a random touch ball that cannot be returned. So, the sample space of the experiment contains 12 sample points, indicating that event R and event G are mutually exclusive. Let's calculate the probabilities of these 3 events separately. I touched the red ball twice, containing 2 sample points, so the probability of event R is to 12th. The probability of event G is also to 12th, as the green ball was touched twice and included in both samples. The 2 touched balls have the same color and contain 4 sample points, so the probability of R and G and the event is for 12th. It can be seen that the probability of R and G and the event is equal to the sum of the probabilities of these 2 events. If we generalize to the general case, we can obtain property 3. If event A and event B are mutually exclusive, then the probabilities of A and B and the event are equal to the sum of the probabilities of the 2 events. The probability addition formula for mutually exclusive events can be extended to the case of multiple events. If events A1, A2 to M are mutually exclusive, then the probability of the sum of events A1, A2 to M occurring is equal to the sum of the probabilities of these M events occurring separately. If event A and event B are opposing events, what is the relationship between their probabilities? Because event A and event B are opposing events, they are inevitable events. That is to say, the probability of event A and event B is equal to 1. From property 3, we can conclude that the sum of probabilities for event A and event B is equal to 1. So we can obtain property 4. If event A and event B are opposing events, then the probability of event B is equal to 1 minus the probability of event A, and the probability of event A is equal to 1 minus the probability of event B. In classical models, if event A is included in event B, That is to say, if event A occurs, then event B must occur. So the number of sample spaces contained in event A must not exceed the number of sample spaces contained in event B. This is the content of property 5, which we call the monotonicity of probability. From property 5, it can be concluded that for any event A, because event A contains impossible events and inevitable events, the probability of event A occurring is greater than or equal to 0 and less than or equal to 1. Next, let's consider this question. In the above example, event R1 represents the first time a red ball is touched, event R2 represents the second time a red ball is touched, and the sum of R1 and R2 represents the presence of a red ball between the two balls. So are the probabilities of R1 and R2 and the sum of the probabilities of two events equal? If they are not equal, please explain the reason and think about how to calculate the probability of R1 and R2 and the event. Event R1 touched the red ball for the first time and contains 6 sample points, so the probability of R1 is 6/12. Event R2 touched the red ball for the second time, containing 6 sample points, so the probability of R2 is also 6/12. The probability of R1 and R2 merging events is 10/12, as there is a red ball containing 10 sample points among the two balls. Obviously, the probabilities of R1 and R2 and the event are not equal to the sum of the probabilities of these two events. The reason is that R1 and R2 are not mutually exclusive events, and their interaction event contains 2 sample points. When calculating the probability, these 2 sample points were repeatedly calculated twice. So we just need to subtract the repeated one. When extended to general situations, we can obtain property 6. Let A and B be 2 events in a random event, where the probability of AB and the event is equal to the probability of event A plus the probability of event B minus the probability of event A intersecting with event B. If event A and B are mutually exclusive, so the probability of A and B crossing events is 0, which is the content of property 3. That is to say, property 3 is a special case of property 6. The content of property 4 is mutually contradictory, and the sum of probabilities of events is 1. Property 1 describes the non-negativity of probability. Property 2 is the probability of a special event. The content of property 5 is that if event A is included in event B, the probability of event A occurring does not exceed the probability of event B. The above are the basic properties of all probabilities that we have learned. Let's take a look at the example below. Randomly draw one card from 52 playing cards that do not include big or small trump cards, assuming event A equals drawing a red heart and event B equals drawing a square card. The probability of both event A and event B is equal to 1/4. So let the first question be that event C is equal to the probability of event C being drawn in the red color, and let the second question be that event D is equal to the probability of event D being drawn in the black color. Because the red color in playing cards includes hearts and squares, event C is equal to the sum of events A and B, and events A and B are mutually exclusive events. According to the formula for adding mutually exclusive events, the probability of event C is equal to 1/2. The second question is that event C and event D are mutually exclusive. Also, because the sum of events C and D is an inevitable event, events C and D are opposing events, so the probability of event D is equal to 1 minus the probability of event C is equal to 1.5. Let's take a look at the next question. In order to promote a new beverage, a beverage production company launched a prize-winning promotion activity by packing 6 cans of this beverage into a box, with 2 winning drinks placed in each box. What is the probability of winning if 2 cans are randomly selected from a box? Let's analyze it first. Winning includes winning the first can, but not the second can. The first can didn't win, but the second can won. Both cans won the prize. These 3 situations. If event A is considered a winning prize, if a 1 is the winner of the first can and a 2 is the winner of the second can, then corresponding events can be constructed through event operations and the problem can be solved using the properties of probability. So winning both cans can be represented by the intersection of events A1 and A2. The winning of the first can and the non-winning of the second can be represented by the intersection of A1 and A2 opposing events. The first cannot win, and the second can win can be represented by the opposing event of A1 and the intersecting event of A2, and the sum of the 3 events mentioned above is equal to event A. Moreover, the 3 events mentioned above are mutually exclusive, so the probability of event A can be calculated based on the probability addition formula of mutually exclusive events. We use a tree diagram to determine the number of sample points for the corresponding event. It can be concluded that the sample space contains 30 sample points, which are 6 times 5, and each sample point is highly probable. So the first can winning and the second can winning contains 2 sample points. The first can wins, the second can does not win, and the sample points included are 2 times 4, which equals 8. The first can does not win, and the second can contains 8 sample points multiplied by 4. Therefore, the probability of event A is equal to 2/30th plus 8/30th plus 8/30th equals 3/5. This is the first method. The above method requires calculating probabilities in several scenarios. Note that the opposite event of event A is not winning, and neither of the 2 cans won the prize, containing 12 sample points equal to 4 times 3. So, the probability of both cans not winning is that 12/30 equals to 5th. Therefore, the probability of event A is equal to 1 minus 2/5, of which equals 3/5. Through the above 2 examples, we can summarize the following points. The first category represents simple events. Based on the relationships and operations between events, simple events are used to represent complex events, and the probability is calculated using the probability addition formula of the sum of mutually exclusive events. Secondly, using a tree diagram can help classify and represent simple events, represent complex events with simple events, and accurately calculate the number of sample points contained in each event. Thirdly, if the probability is directly calculated. The situation is quite complex and can be solved using the indirect method with the help of opposing events. Next, let's make a summary. In this lesson, we learned the basic properties of probability, including the non-negativity of probability, probability of special events, the additivity of probabilities for mutually exclusive events, the probability and uniqueness of opposing events, the monotonicity of probability, and the method for calculating the probability of events. That's all for this class. Goodbye, everyone.